part of our lecture, MIMO Control 2, we want to discuss the so-called Smith-Macmillan form of a transfer function matrix. And yeah, first of all, let's discuss what is the transfer function matrix. It's a complex representation of the system, and you have a matrix with those transfer functions, so G11 for instance, and G12, G21 and G22. And what we would like to do is we would like to transform this in a matrix M, which is still a complex, but what is a diagonal matrix? So we would like to cross out these parts somehow for this transformation. As you know, our transfer function matrix G from S does not has to be a square matrix. It might be that the number of rows does not represent the number of columns, and that's why our output M from S does not have to be a real diagonal matrix. It might be that it's a pseudo-diagonal matrix. So yeah, and what do we do? You use approaches from simple mathematics to conduct this transformation, and it's easier to describe this on an example. So first we just imagine a transfer function matrix G from S, and let that be 1 minus 1 S squared plus S minus 4 and 2S squared minus S minus 8 and S squared minus 4 2S squared minus 8. Okay, this is our starting point. And what we see right now, this will not be, it will be not possible to transform this in a perfect diagonal matrix because we have 3 rows and just 2 columns, but that doesn't matter. We will transform it in that way that the location 1, 1 and 2, 2, there will be parts within the matrix, and the remaining 4 variables will be transformed to zeros. How do we do this? The first thing that looks pretty simple is that we could cancel out the location 1, 2 by adding column 1. So we do one thing. We say column 1 plus column 2, and we assign that to column 2. And what we get is, so we keep the first column, so it's 1 S squared plus S minus 4 S squared minus 4, then 0. That's our first approach. Then we get 3 S squared minus 12 and 3S squared minus 12 as well. Okay, so we came a bit closer. The next thing we do is we will subtract from row 2 row 1, but times the part that stays in here. So we say row 2 minus row 1 times S squared plus S minus 4. And we assign that to row 2. and to the new row 2. And what we get is we will cancel out the location 2, 1 completely. So we get 1, 0, 0. Furthermore, we get 3s squared minus 12, s squared minus 4, and 3s squared minus 12 again. So, and the next part is we will take row 3 and subtract, so we will do actually the same thing again. We will take row 3 and subtract row 1 times the location in 3, 1. So next thing we do is we say row 3 minus row 1 times s squared minus 4, and we assigned it to row 3 new, and what we get is 1, 0, 0, 3s squared minus 12, then 0, that's what we want to do. And in this part, no change will happen, so it's still 3s squared minus 12. Okay. What we can see within here clearly is that row 2 and 3 are equal. We can just subtract them from each other and assign the result to row 3 again. And then we will have zeros in here. So row 3 minus row 2, and assign that to row 3 new. And then we are nearly there. Then we have 1, 0, 0, 0, 3s squared minus 12, and 0. And the only thing that we will do is we will get rid of this 3 by dividing row 3 by row 2 by 3. And then we are finished, and then we will get m from s, which is our Smith-Macmillan form of this transfer function matrix, and this is 1, 0, 0, 0, s squared minus 4, and 0. All right. This is our first result. We can now analyze this representation about zeros and poles, and the zeros and poles of this diagonal, they are the zeros and poles of the whole system. And what we have to remind us that the system characteristics might not be completely equal to the characteristics of the single transfer functions. So when we look in here, and we would analyze this all these transfer functions for zeros and poles, we will get a set of poles and zeros, but they do not have to be equal to these poles and zeros, because the system has some different characteristics, and that's why we have to use this approach. So, all right, and in the next slide we will do another example, and then we will analyze those examples for zeros and poles again. Now we want to discuss a more complex example. We will imagine a different transfer function matrix that has more inputs, and then we will analyze the system. First thing, we assume that we get g from s, and we let it be 1 over s squared plus through s 3s plus 2 and minus 1 over s squared plus 3s plus 2, then s squared plus s minus 4 over s squared plus 3s plus 2, and then plus 2 s squared minus 8 minus s, and finally s minus 1 over s plus 1, and 2 s minus 4 over s plus 1. So, done. Right now we would be able to analyze the single transfer functions for zeros and poles. Let's take the part in location 3, 1. And let's analyze this. For instance, we have s minus 1 over s plus 1. From here we get the zeros when this is 0, and when this is 0 we have the poles. And this will be a pole when s is minus 1, and this is a 0 when s is plus 1. So that's easy to understand. Yeah, and we will just keep this in mind and look whether the whole system has the same zeros and poles. How do we analyze this? Yeah, we have to use the Smith-Macmillan transformation again. You can have a more closer look at the provided script. There is a step-by-step description of how to do this. Oh, I just forgot something. 3s plus 2. Now it should work. And yeah, and I will just provide you the Smith-Macmillan transformation. You know how to do this. And this will be 1 over s plus 1 times s plus 2. Then 0, 0, s minus 2 over s plus 1, and then 0, 0. So that's it. And now we can analyze this system for zeros and poles. The first input will be will not reveal us anything about zeros, because this part will never be 0. So that's it. The second part, there might be a 0, and it might be 0 when s is plus 2. And that's it. More zeros won't be there for the whole system. And when we compare this to one part of the system, we see that the given 0 isn't there. So there's a difference, and that's why we did this analysis. All right, now we can analyze the poles as well. And what we will get is for s minus 1, for s minus 2, and for s minus 1. Okay. And there we see that for the poles especially, we can see that the single poles, they will be, or the poles of the single functions, they will be seen as poles for the whole system as well. But that does not apply for the zeros. So let's write down the most important points from this video. The zeros of G. The zeros of G are it's possible that they are different from G elements. From zeros of G elements. That's important, and the next important point is that also we would like to call them multi-variable zeros. All right, and the next thing we would like to add is that the poles of G are the poles of G elements. All right, thanks for watching.